So again, let the set Z be the set of all natural numbers, or 0, or an additive inverse of a natural number, and let A and B be whole numbers. Now, if A is greater than B, then A plus the additive inverse of B is a natural number, which is a subset of Z. If B is greater than A, then A plus the additive inverse of B is the additive inverse of some natural number, which is a subset of Z. And if B is equal to A, then A plus the additive inverse of B is 0, and so this is in the singleton set containing 0, which is a subset of Z. So in any case, A plus the additive inverse of B is an element in the set Z. Now we have also seen that the additive inverse of A times B is the same as A times the additive inverse of B, which is the additive inverse of the product A times B. This is either the additive inverse of some number or 0, and this of course is a subset of the set Z. And the product A times B is the same as the additive inverse of A times the additive inverse of B, which is the additive inverse of the additive inverse of the product A times B. And so this is a whole number, which is a subset of the set Z. So we have just indirectly demonstrated that it is always possible to add, subtract, and multiply the elements in the set Z and remain in the set Z. And so we can be confident that the set Z under normal addition and multiplication is a ring. It is, of course, possible to rigorously demonstrate that Z under normal addition and multiplication is a ring, but it is much less straightforward and less elegant than the quotient set construction that we use for the integers. So let Z, again, which is all natural numbers, or 0, or the additive inverses of the natural numbers, be equipped with normal addition and multiplication. And for clarity, normal means the addition and multiplication that you learned in secondary school. Then the function phi from the integers into the set Z, defined by phi of the equivalence class of the ordered pair AB is A plus the additive inverse of B. This function is a ring isomorphism. So proof. Suppose that phi of the equivalence class of the ordered pair AB is the same as phi of the equivalence class of the ordered pair CD. Then A plus the additive inverse of B is the same as C plus the additive inverse of D. Now we can add we can add B and D to both sides of the equation. And so we will have that A plus D is equal to B plus C. This means that the ordered pair AB is equivalent to the ordered pair BC, CD. And so the equivalence class of the ordered pair AB is equal to the equivalence class of the ordered pair CD. And thus, the function phi is injective. Since phi of two different elements are equal if those two different elements are in fact the same, or what appear to be two separate elements. Okay, so now let A plus the additive inverse of B be an element in the set Z. Then A and B are whole numbers. And so the ordered pair AB is in the Cartesian product of the whole numbers with itself. And hence, the equivalence class of the ordered pair AB is in the set of integers. That is, there exists an equivalence class of the ordered pair AB in the set of integers such that phi of this equivalence class is the element A plus the additive inverse of B, and thus the function phi is surjective. Surjective. So since the function is both injective and surjective, the function phi is a bijection. So there's a one-to-one correspondence between the elements in the set of integers and the elements in the set Z. So we now need to show that the properties for addition and multiplication hold. That is, we calculate phi of the sum of the equivalence class of the ordered pair AB plus the equivalence class of the ordered pair CD. This is phi of the equivalence class of the ordered pair A plus C, B plus D, which is A plus C plus the additive inverse of B plus D. The additive inverse of a sum is the sum of the additive inverses. And so we have A plus C plus the additive inverse of B plus the additive inverse of D. And we can regroup these terms so that we have A plus the additive inverse of B plus C plus the additive inverse of D. So we can group these terms so that we have phi of the equivalence class of the ordered pair AB plus phi of the equivalence class of the ordered pair CD. And so the addition property holds. So next, we will calculate phi of the product of the equivalence class of the ordered pair AB times the equivalence class of the ordered pair CD. And this is phi of the equivalence class of the ordered pair AC plus BD as the first coordinate, and AD plus BC as the second coordinate. And so that is the sum AC plus BD plus the additive inverse of the sum AD plus BC. And so we have AC plus BD plus the additive inverse of AD plus the additive inverse of BC. So now let's calculate phi of the equivalence class of the ordered pair AB times phi of the equivalence class of the ordered pair CD. So we have A plus the additive inverse of B times C plus the additive inverse of D. So we have A times C plus the additive inverse of B times C plus the additive inverse of A times D plus the product B times D. So note that this is the same AC plus BD plus the additive inverse of AD plus the additive inverse of BC. And so we have that phi of the product of the equivalence class of the ordered pair AB times the equivalence class of the ordered pair CD is the same as phi of the equivalence class of the ordered pair AB times phi of the equivalence class of the ordered pair CD. And so this function phi satisfies the definition of a ring isomorphism, and therefore phi is a ring isomorphism. And so the set of integers, as we modeled it as the quotient set, is the same, is algebraically, is isomorphic to the set Z of the set we normally think of as the integers. And so we can choose to use that model for the integers. That is, we choose the set Z to be, the set of integers to be what we normally think of as the integers, 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on. And so every fact that we established for the set of integers modeled as the quotient set is true for this set for the integers modeled as this set with normal addition and normal multiplication. And this is allows us to keep all the elements on a single line. Which is our geometric model for the real line. And so going forward, when we speak of the integers, we mean this set with normal addition and normal multiplication. And we have demonstrated that this is an integral domain where the left and right cancellation laws hold. And as we mentioned, an integral domain is not a field because not every non-negative element has an additive inverse. It's not always possible to divide elements. So let's make a new definition. Let A and B be integers. Then A divides B and this is denoted A divides B, if there exists an integer k such that B is equal to k times A. So for example, 7 divides 14, since 14 is equal to 2 times 7. So our next step is to use the integers to construct a field where it is always possible to divide the elements and remain in that same set. And the field that we will construct with the integers is called the set of rational numbers. And so moving in that direction, we're going to construct the rational numbers in a manner similar to the way that we constructed the integers as a quotient set. So in order to do that, I'm going to leave it as an exercise for now. Let the set z star be all integers except for 0, and define a relation tilde on the products on the Cartesian product of the integers with this set z star, and define that relation by the ordered pair AB is related to the ordered pair CD if and only if A times D is equal to B times C. So rather than A plus D and B plus C that we use in the construction for integers, we have A times D is equal to B times C. So prove that the relation tilde is an equivalence relation. Okay, so we will end here for now. Next time we will construct the rationals and look at the algebraic properties, and also bring in some new properties, which are the order properties. So I hope you have enjoyed the 8th lecture. Thanks for watching.